Sure. So my research, my thesis, which I recently completed, is on scheduling with multiple robots. So if you have a bunch of robots in a building, like our CoBot robots, which go through our office building picking up and delivering items, the question is which of these many robots is going to pick up which item at which time, and when is it going to deliver it? So this problem is NP hard. We have lots of algorithms to figure out the scheduling of these. And this also applies to other problems like autonomous taxis, ride sharing, and robots working in factories. So my responsibilities are mainly doing my research. Then I also help working on maintaining these CoBot robots, particularly the things related to the scheduling of them and the multiple robots. And Joydeep here, he works on the lower levels of these robots.
Yeah, so my research is on how do you get these robots to handle changes in the environment. In particular, human environments have things which are static over long periods of time, like the walls. The walls don't move. However, things like tables and chairs, which the robot sees on a daily basis, they move around. And where you see the tables and chairs to be today is not indicative necessarily of where they will be exactly tomorrow. And if you're in a cluttered environment, most of the thing which the robot is actually observing are these movable objects. So my research is essentially on how does a robot reason about these movable objects and still be robust to figuring out where it is in the building over a long period of time. I also work on another project, which is the robot soccer project, which essentially deals with how do you come up with interesting coordination behaviors across an entire team to perform a coordinated task. And soccer is just an example. We use soccer as an example to test out some interesting ideas. So in soccer, the ultimate goal is, of course, to score goals. But then to be able to successfully score goals, you need to actually perform a lot of intermediate tasks like passing and dribbling and so on. So how do you frame these intermediate goals in terms of the entire multi-robot team framework? And these are some of the challenges that we're looking at actually. Apart from these two research focuses, I also work on maintaining the actual hardware of all the robots, making sure everything's up and running. In fact, we maintain a 5-minute demo rule in our lab where essentially if you have visitors, within 5 minutes we would like to be able to give a demo of live running robots to anybody who visits our lab. And that means that we have to keep all our robots up and running pretty much all the time. So Manuela has actually a bunch of students working on a very wide range of interests. And they all somehow relate together to having robots be autonomous and reliable and robust in everyday life. But the specific focuses that each student work on, they vary a lot. So Brian works on scheduling, I work on the actual perception of these robots and the navigation planning and so on. Another student, Juan Pablo, he's working on how do you detect failures that you did not account for and cannot account for. Max Curry, and he's also a Ph.D. student, he's working on how do you essentially schedule tasks by the robot to come up with ways of improving the task performance in the future. So it's kind of like practicing certain things in its free time, and the robot needs to be able to do this on its own. Richard is another PhD student who is doing work on working with Wi-Fi signal strengths, seeing how we can come up with better network topologies now that we have a robot that can actually actively measure these signal strengths across the buildings. We've had some really interesting work with having these robots acquire information from the web. This was work done by student Mehdi, and he actually looked at how do you extract information from the unstructured web. So if someone asks a robot to bring me a stapler, the robot doesn't know what a stapler is, but the robot does know that the building has a kitchen, the building has conference rooms, it has offices, it's got supply rooms. So it tries to look to the unstructured web to try and figure out which is the most likely location to find this object stapler. and it does this, and then it figures out that it needs to go to an office and so on. There are also other students, Susanna, who's working on active perception. So if you have, if you're looking at two different objects and they look the same from one different side, which way should you turn the robot to look at the other sides of the object so you know that it's A and not B, so on.
So we also have Danny Zhu, who's been working on, for the small size robot soccer, an autonomous referee. Right now a lot of that functionality is done by humans, calling when the ball is out of bounds, who kicked it out of bounds, where it goes in next. He's working on making that all automated. We also have Junyoon Tai, who's a joint student in Singapore, and she's working on like autonomous dancing to music, figuring out the dance moves automatically and doing things based on that.
So we also have Vittorio, who's a new PhD student in computer science. He's looking at how do you interact with the robots with speech. Speech is one of the most often requested tasks with the robots. Humans want to interact with the robots not with the touchscreen or with commands on the web, but rather by giving it spoken commands. And that is actually pretty difficult if you're not in if you're not in a lab setting, if you're not in a quiet environment. If you're in a crowd and there's people talking around you, how do you listen to only one person, and how do you adapt to the different forms of requesting a task? Instead of saying, can you bring me a coffee? The person can say, please bring me a coffee. Some person might say, I would like a coffee, please. And still all of these map to the same task, which is bring me coffee. And his work is essentially on figuring this out.
We also have a few students who just graduated. Fatma Farouk, who's working with the Baxter on picking up objects. Then we have Prashant Reddy, who is working on learning to play energy markets, so that you could have like solar power generated from your home, and you could have agents which sell these to the general market and make everything work more efficiently for everyone. And we have Philippe Trevisan, another student who recently defended his thesis, who's working on more traditional planning. So he introduced these fast algorithms to make plans for CoBot to find objects in the building and other more general planning problems.
So you can see that we actually have very wide regions of areas of interest. They are somehow mostly connected to robots. Some of them are a little bit less connected to robots, maybe like the energy fields, but they all involve improving intelligence and autonomy in the real world.
So a couple of years ago, we took a robot census at CMU, where we had to count all of the robots in our lab. And I think then we had 160?
100 and something robots in our lab.
Yeah.
Not all of them are in active operation. In active operation, we have two labs. In the 7th floor lab, we have 4 CoBots, which are collaborative robots. They work with humans. We have 12 small-size soccer-playing robots. These are all active robots. In the other lab,
we have the one Baxter. We have several CoBots, which are being used a little bit. And then we have many Naos, I think like 10-ish. And then we also have a bunch of robots we don't use. A lot of IBOs, which are the dog soccer playing robots. Maybe like at least 30 of those, I think. And then we have a bunch of educational robots like Lego Mindstorms and other similar things.
So there's also a reason why we have so many robots. It's because Manuela's interest isn't just with working with one robot, it's also with how do you have teams of robots interacting and cooperating with each other. So in a soccer team, we don't have just a single robot playing soccer, we have a team of 6-on-6 robots playing soccer. We don't just have a single CoBot performing task, as Brian mentioned. He performs scheduling for multiple robots, and how do you divide up the task across robots, which is why it's actually important for us to have a large number of robots. There's an alternative method of working with robots where you have one really expensive, really capable robot, or you can have many robots which are not necessarily all that expensive, necessarily not all that not the most expensive sensors, not the most expensive manipulators, but together they work in cohesion to be able to perform tasks on a larger scale. So almost all our robots run software on pretty much commodity computer hardware. So the cobots have just regular laptops on them, and we just write programs for the perception, cognition, and action for those robots. For the small size soccer playing robots, they are controlled by one desktop computer off board by radio, and I guess they have as much of a soul as any regular desktop or laptop computer has. And yeah, I think that's kind of what we do with the cobots and the small size soccer robots. There's a very wide range. So from the lowest levels, the motor drivers are written in C. Going slightly higher up, the perception processing is done in C++ because it needs to be pretty fast and pretty optimized. For the higher levels, we use Python for actually excuse me, for figuring out how do you interleave tasks between each other and actually doing task planning, because that doesn't need to be necessarily computationally intensive. On the web interface, Brian can actually give a better idea.
Yeah, so there it's mostly Python as well as some JavaScript, client side things. We also, in some of our other projects, we use other languages like Java we used for the Naos for a while. We have students using more functional languages. I think Philippe uses.
Yeah.
Not sure exactly. So basically, whatever language is the best fit for the specific task we're doing.
Our robots are pretty reliable and safe when they're operating on their own. In fact, the robots, only when joysticked by humans do they actually hit objects. When they're entirely autonomous, they are always safe. We actually err on the side of caution. So if the robot is uncertain as to whether an action that it's trying to take is safe or not, it'll just stop and not take that action. It'll try to look for an alternative action that can take. So in that sense, it's actually very safe in terms of obstacle avoidance. However, the problems that we face are sometimes, because we might be erring on the side of caution a bit too much. There's one very common example which we keep on encountering in our building. There's this one narrow hallway, and there's this one plant, and the plant sometimes droops over onto the hallway, and the robot doesn't know what a plant is. It just knows that there's an object in front of it and it should not hit it. So then it knows that there's a hallway, and it knows there's an object in the middle of the hallway which is presumably human or movable. So it'll just stop for the plant and say, please excuse me, to the plant. So in that sense, adding more domain knowledge to the robot would actually help doing some more interesting obstacle avoidance, which we are looking at in the future, but that's where we're at right now.
So yes, I think they could, but that adds a lot of new challenges. If you add a hand, you're going to miss things you want to. So the main reason we would want to add a hand is so that we could push elevator buttons. Right now, when CoBot wants to take the elevator, he'll ask a human for help. This is Stephanie Rosenthal's Ph.D. thesis work called symbiotic autonomy. So the idea is that the robots are really good at doing some things, humans are really good at doing some things. Let's have them help each other out. So the CoBots don't have arms, so they can't press elevator buttons. So they'll ask humans to press those buttons for them. And if we had hands, then we could press them ourselves, and we wouldn't need to inconvenience the humans. But what we realized when we were developing these CoBots is that if we want them to be perfect and to do everything right all the time, right now, it's never going to happen. So the idea is that we can, for the things we can't do with the robots, we'll get the humans to help so that we can at least have the robots deployed in the building, doing robustly what they're able to do now. And we can not have to wait 10, 20 years for everything to come together.
So that's actually a point which cannot be underestimated or understated, because if we did not actually ask humans for assistance, our robots would be confined to a single floor in the building. Since the robots are willing to ask for assistance, they are able to traverse the elevators and go to multiple floors in the building, and also different buildings, in fact, which are connected by bridges. And since they're willing to ask for assistance in things like, could you please take the printout from the printer and put it in my basket, it can do more complex tasks like delivering mail, picking up objects from the different offices, taking them to the main office. In fact, when I was building the new small-size soccer robots, I would frequently get mail orders for parts for these robots, and I would send it to the main office with the task that just bring the parts which I have gotten in the mail. I don't need to do that. The robot can do that for me.
And over time, we've also greatly reduced how much we need to ask for help. So originally, to localize, the robots would get lost all the time going through the hallways because they were localizing with Wi-Fi. And the robot would always stop. He'd ask the human, where am I? Please press on my screen on the map where I am. And now with Joydeep's new localization algorithms, the robots never need to do that anymore. So we're hoping that as we go on, there will be less and less times we need to ask for help, and the robots will be more and more autonomous. So I think one of the biggest things that's missing is really robustness and reliability for our robots. So in robotics, a lot of times you'll come up with some great new idea, you'll write a paper on it, you'll take a video of it, and then you'll say you're done. Even if that video worked maybe 1 of the 10 times you tried it as it's supposed to work. And there really needs to be more emphasis on making things work more often in conditions you weren't expecting them to work in. So our CoBots, they really have to do that. As Joydeep mentioned before, we want to be able to deploy them within 5 minutes of anyone showing up at any time with anything happening in the building. So, and sometimes things happen which we weren't expecting. Like one time, this is fairly common actually, but we'll send CoBot to go somewhere. There'll be someone working in the hallway, and they'll have some big cart blocking the entire way, and it might be something CoBot can't detect because it's not at a sensor level. This was a very big problem. There were some tall tables, which are this high, above CoBot's Connect, and CoBot kept running into them. So what we did was we added another Connect on the floor level, which points upward, and now CoBot doesn't hit those tables. But really, you only find these problems if you're deploying the robots all the time and seeing what goes wrong in the real world.
Yeah, I think unless you actually try deploying your systems in real life situations over and over and over again, you cannot be sure that you have actually addressed the main concerns. Like when you're coming up with your own theory, you can think of these are the problems which I'm likely to face. Now, is it really true that the problems that you thought that you're likely to face are really the problems that your robot encounters? I mean, it's very difficult to know that a priori until you actually start deploying a robot. In addition to the robustness thing which Brian mentioned, I think a lot of people are realizing that instead of having an algorithm which can work really, really well 99% of the time and totally fails catastrophically 1% of the time, it might be better to have one algorithm which works 100% of the time, not necessarily as well, but much more consistently. And the reason for that is that the longer you deploy these robots, the more likely that you're going to encounter these edge cases. These edge cases which people assume are, this is an assumption that we're making, which is not going to be satisfied and so on. Things will happen which will make you reconsider your assumptions. You think that every obstacle can be observed. That's not true. You'll come across obstacles which cannot be detected by LiDAR or by vision or by sonar. And then what do you do when you hit them? You just have to recover. Maybe a part of the way we should work with robots is also not necessarily having to work with algorithms which are 100% accurate or 100% reliable, but rather algorithms which can recover gracefully. Humans themselves are not perfect. Like humans run into glass doors all the time. But the thing is that we recover really well. We get out of the elevator on the wrong floor, we realize really quickly that we've gone on the wrong floor, and then we recover. I think our robots need to be better at recovering gracefully.
No, I don't really think it's overwhelming. I think there's a lot of variance in how many papers people publish. So like our lab is probably on the mid-higher end of the scale on numbers of papers we publish, and that's great. But there are also people who they'll publish one paper a year, but they'll put a lot more effort into that paper, and it'll be much more thorough and impactful than any single one of our papers. And what are the greatest challenges? So I just graduated last month, so I'm on vacation, and it's not very challenging.
I think one of the challenges which I find is that we have robotics is not an isolated field anymore. We have hundreds of thousands maybe of labs working on similar problems across the world, and we tend to work kind of in isolation. Like when we're working on one research problem, when I'm working on my own research, I do not consult with intimately with the other group. And because of that, what we sometimes find is that we come up with similar ideas spread across geographically from different places, which is also why we, if you notice recently, we have thousands of papers published every year. A number of them are exploring great ideas, but some of them have very good overlap with each other. I wonder if it would be possible to have some sort of better collaboration such that we don't have duplication of efforts. It's good to have corroboration of efforts, but on the other hand, to rediscover something separately over and over again, maybe we can do better. I think we are moving pretty quickly into the point where robotics is not necessarily for group of researchers in academia, whereas but more to along the lines of anybody with access to hardware and a computer should be able to duplicate your efforts. We have a bunch of hobbyist roboticists, and they would love to have access to what people have looked at, what research people have done, and try to replicate them. And that's one way of looking at it, that everybody should have access to information and the latest cutting level research. You shouldn't have to pay hundreds of thousands of dollars, which is why open access is really important. And the second thing is, which I've heard mentioned, and I kind of agree with, is that in many of the cases where these large sums of money are transacted on, it's actually the government's money, which is ultimately the taxpayers' money. So in that case, the taxpayer should have access to the results of this research, in which case the open access makes much more sense. And I'm glad that this is actually consciously becoming an issue today, and lots of people are publishing to open access journals and conferences.
Yeah, so I agree with Joydeep that open access is definitely where we should be, but I haven't personally published any open access papers. Have you?
So I think a bunch of the conferences and journals have guidelines as to what you can do to release in a timely and relevant manner the same papers that you publish. So journals which don't necessarily, even journals which are not primarily open access would have policies on this version of your journal can be released on your personal website for open access. It might not necessarily be that the main journal access website is open to all, but on the other hand, you can have a copy of your own work for dissemination personally on your own personal website. And that's not necessarily open access and from the journal or from the conference standpoint, but at least it's providing open access to your information. And if people can access your information, I think that's good. It doesn't necessarily matter which different channels they have to go through, as long as they're all legal and sanctioned. I was interested in the idea of having an intelligent agent or a machine which could actually think about, observe the environment, think about what's happening and what its goals are, and actually make changes to the environment in itself. I got involved with robots, with competition robots like Micromouse, which is a robot which needs to traverse an unknown maze. And the interesting parts of it were, to me, were that there's something which is unknown to the robot. It doesn't know what this maze is. It has a fixed goal. It needs to get to the center of this maze, and it needs to do this in a really, really fast manner because, well, that's the goal of this competition. So I got hooked on this because it's a very well-defined problem. It's challenging enough, and it's a very high-performance robotics application or robotics competition, because the world leaders in this finish an entire maze, compete in an entire maze, and complete an entire maze in like 7 seconds or 5 seconds. However, moving on from there onwards, I started looking at how these robots can actually help people in indoor environments, and I think that's going to be an important thing. There are lots of people who would appreciate assistance in doing tasks in indoor environments. There are cases where humans don't like to do certain things, and robots could easily do those. Well, not necessarily easily, but should be able to do those things. Like, I see people shoveling the sidewalk in the cold winter, and I think to myself, well, shouldn't a robot be doing that? Shouldn't we be making robots to do that? And I think that's one of the main reasons why I'm interested in working with robots.
That's a tough one. It's probably a combination of a bunch of people. I guess starting with my parents, then my advisor, Manuela Veloso. As an undergrad, I worked in the robotics club on this colony of robots, it was called. There are a bunch of really cheap robots. We had 12, I think, that could do very little. They had like a few range sensors and a 2-wheel drive, and probably that's what most got me into robotics.
I think working towards a PhD degree involves tackling certain known unknowns and tackling certain unknown unknowns. Let me clarify. So you know that you're going to solve a particular goal. You're going to have a robot which is robust to changes in the environment. What you do not know when you first set out on that is that you're going to encounter a bunch of problems which you did not even anticipate. And not only did you not anticipate encountering those problems, and when you first encounter them, you do not know immediately as to what will be the method to solve them. And I think one of the skills that a researcher needs to develop while on the track to getting a PhD is how do you nimbly adapt to these unknown unknowns, and how do you tackle them, or at least come up with ways of circumventing them. Risk minimization is, I guess, what people call it. And also the other thing which I am passionate about, and it's still challenging, is that I want to have these robots be actually working in the environment on a continuous time scale over months and years. So that puts a lot of pressure on us to actually do a lot of engineering in the system. So our robots perform a lot of self-tests and diagnostics. In fact, I am at this conference today, but however, my robots, every night, they're still sending me reports as to the logs that they process. They might not actually have moved anything because everybody's at the conference, but they still process the logs, make sure that the code is up to date, make sure everything's compiling, make sure the tests are succeeding, and so on. And all of this engineering is important, and it takes a lot of time, and that time spent on this engineering doesn't necessarily contribute directly to research or directly to papers. However, it makes it easier to do research in the future because I need to collect data for thousands of kilometers, and if I didn't have this robust system, I would not have been able to do it. So engineering is a very integral part of getting a PhD thesis in robots, if you want to work with real working robots, that is.
So I guess probably the most challenging thing for me was not to get cynical about it. So I would work on something for a long time, it wouldn't work, I'd try something else. It would sort of work. I'd eventually make progress on things. Sometimes I'd be like, oh, my entire area of research is pointless. No one will ever use this. Which isn't true, by the way. But yeah, so basically, like, just keeping at it is the hard part.
I think I would be most interested in working with research with robots, real working robots, and the lines between research in industry and academia is blurring quite a bit, because both research and academia as well as industry is looking at interesting applications, real robots, and similar problems. So in that sense, I don't think there's as much difference in terms of what kind of research you will do and what kind of robots you will work with in academia versus industry. I'm actually open to both of these options, and I will be actively pursuing both of those options and picking the best one when I get multiple options.
So I've chosen a current industry. I'm starting at NASA Ames Intelligent Robotics Group in August. I don't think there's just necessarily one person who influenced my career the most, but I think it'll be a large group of people. I think definitely first and foremost my parents, who always motivated the question of inquiry, like posing difficult questions or posing quizzical questions, and having me think about what it means to answer those questions. And that helped progress my inquisitiveness in science in general. And as I got to meet more people, it's always interesting to talk to people and discuss ideas with them at CMU and in my undergrad university. So I don't think it's just one person who has influenced me, but it's an accumulation of a very large number of people who have had great discussions with so far. So probably if I had to name one person, my advisor, Manuela Veloso, just because I've spent the most time working with her. She's influenced me a lot.
I'm sorry, I don't think I can name 5 roboticists and pick them out and say that these are the 5 best ones. I think everybody does great work on their own, and I think we need to value everybody's work for what it is. I'm going to cop out of the question like that.
That's a tough one. It's not like name your favorite cartoon character or something like that, because they're like people I know. It's not a very big community, as some people might expect. So like, I guess Joydeep's one of my favorite roboticists. But
I think one of the things which I value the most from my advisor is not only the how do you do research, but how do you get your research to work with real robots and actually applying them. So it's okay that you're doing great research and coming up with great theory, but then if you're not able to show it demonstrated with real working robots, it doesn't really, at least to Manuela and to me now, it's not as great of a value. There are a couple of reasons to that. One of the main things is that unless you actually work with a real system and demonstrate working with that on a real system, you can't claim that you have thought of the actual problems that you've had. In some cases, when we try to do something and it does not work out in the way that we expected, like supposing I'm trying to solve this problem and people have told me that POMDBs are totally the way to go to solve this problem. And if the POMDBs don't work out, then I have learned from Manuel that you shouldn't try to like really shoehorn the POMDB in to solve the problem. Maybe you should just step back and try something else, try something totally different. And it's okay if people don't agree with your approach to doing it. If you can solve the problem, you have solved the problem. A friend of mine had once told me that every hack has a theory behind it, and it's okay. And I now realize that it's okay to come up with a hack and get it to work with a hack, as long as you come back later and look at why that hack worked. And working with robots is really about solving problems. It's not about just coming up with beautiful math theory and all. You need to have working robots at the end of the day.
So probably actually nothing to do with robots. It's I'm a very shy person by nature. She is not. She knows exactly what she wants, and she will get it no matter what. And if someone disagrees with her, then they're gone. So basically to be more stubborn in a good way.
I think you might hear this from a lot of people, but my favorite fictional robot would still be Rosie, just because she's so dexterous and capable of doing so many different things, handling the kids, handling the dishes, handling chores around the house. And it's probably a very impractical dream, but still we need to have impractical goals so that we can make something practical, which is awesome.
I guess it's a bit obscure, but one of my favorites is from iRobot. There's this robot, it's on Mars, and it needs to get something from this lake so that the human inside won't die. I forget exactly what it was. But this guy, he tells the robot, okay, go get this thing from the lake. And then the robot goes to get it. But the lake is really hot, and if the robot goes into the lake, there's a risk of it getting destroyed. So he has these two conflicting objectives: stay alive and bring this thing back. So what the robot does is it just walks in circles around the lake forever. And I think that's really what robots are like now. Part of the problem is we don't even know exactly how to formulate what the robot's to do. Given what we tell them, they execute it reliably every time, but we might not give them the best instructions. And there's no matter whatever they do, there's going to be some trade-off. And we need to think rigorously about how to do these trade-offs, what exactly we want the robot to do, and how to give these instructions.
I don't know. I think you've already, based on your questions, I think you've already come up with the most important things that you pointed out, the idea of open access, which is great. I think you have also looked at the duplication of research efforts and all. I think what would really be nice is that if you made it easy for researchers in robotics to be able to share code and data. Robotics is all about seeing how we can transfer what we have learned with one set of system on one robot to another robots and so on. And it's not necessarily that easy to do, because one computer is very similar to another computer, but two robots are very different from each other depending on who's constructed them, how they constructed their mechanisms, and so on. So it would help to have certain, when someone comes with a publication or some algorithm or some great approach, it would be great to have a standard data set for that approach, for each approach. And instead of just having a single publication, the publication should be associated with the data sets that came with it. Then knowing that there might be certain licensing restriction, that might not be possible to have open code to that the algorithms, which would be great as well. But even if there is no open code, it would be great to at least have a closed binary. And if we had that, then that would actually provide me as, for example, a reader, to look at this paper and say, wow, this is really good work. How do I get quickly up and running? And then if that paper was associated with open data as well as a binary, then I could just quickly run on my laptop and say, yes, that's exactly what I want. Now let me see if I can implement it or make changes to it and get it to work on my own system.
Congratulations. Good luck.
Happy birthday, IJARS.
Happy birthday to the International Journal of Advanced Robotic Systems.